Welcome to solverfy.
Okay, so in this problem, we're talking about retinal and specifically the amount of energy we need to break certain bonds in retinal, specifically the pi carbon-carbon double bond. All right, so the piece of information it gives us is that the bond dissociation energy is equal to 200, sorry about that, is equal to 250 kilojoules per mole. Okay, so now the first thing we're going to do is figure out how much energy we need to break a single bond, not the molar quantity. In order, what to do is we're going to call that energy, and we're basically going to have this 250, and we're going to multiply that by 1,000, and what that's going to do is, not 100, 1,000. What that's going to do is give us this in terms of joules and not kilojoules. To deal with the moles, what we're going to do is divide this by Avogadro's number, which is 6.02 times 10 to the 23rd. And that's going to give us just joules as our unit. So if we do that calculation, the value we come up with is 4.15 times 10 to the negative 19 joules. So really not much energy is required to break that bond at all. Okay, so now we get to delve a little bit into the world of quantum, which is not something you get to do very much when you're doing organic chemistry. And we can say that the energy is equal to Planck's constant h times the frequency. But we don't want frequency, we want wavelength. And we know that we can also convert this to be h, Planck's constant, times c, the speed of light, over wavelength. All right, so then I can say pretty simply that the wavelength is equal to hc over E. Okay, so now that I have that, I can say that the wavelength, and I can just plug in values. So first I've got Planck's constant, which is 6.626 times 10 to the negative 34. And then times the speed of light, which is 3.0 times 10 to the 8th. Divided by the energy, which we said earlier was 4.15 times 10 to the negative 19. All right, when I do that, it gives me a value of 4.79 times 10 to the negative 7th meters. All right. So the question asks for this in nanometers, so this is just equal to 479 nanometers. And if you check, this is just right within the visible range. I believe it's on the lower energy level, so it's going to be closer to red light that's going to do that.